Hello friends, today we will see Harvard and von Neumann architecture. Harvard architecture and von Neumann architecture are two fundamental computer architecture that define how a computer system is organized and how instructions and data are processed. Harvard architecture. This is the block diagram of Harvard architecture. The Harvard architecture is a computer architecture that uses separate memory pathways for instructions and data. So this is a CPU and this is a memory portion for program storage, and this is a memory part for storing the data. This means that it has distinct memory units for storing program instructions and data, allowing simultaneous access to both. That means in this architecture it is possible to fetch instruction as well as data at the same time. Parallelly you can fetch instruction and data. In other words, the instruction memory and data memory are physically separated. This architecture typically results in faster and more efficient execution of instructions, as the processors can fetch an instruction and access data at the same time. The Harvard architecture is commonly found in the embedded systems, microcontrollers and digital signal processor, where the device has to be made faster, a real-time operating system. In that cases the Harvard architecture is used. Von Neumann architecture. In this case, this is the block diagram. Here you will see that the data memory and code memory is the same, and there are two separate buses, one is for data and one is for address. The von Neumann architecture, also known as the stored program computer architecture, this is named after the mathematician and computer scientist John von Neumann. It is characterized by use of single memory unit that holds both program instructions and data both. In this architecture, instructions and data are fetched from the same memory location and processed sequentially by central processing unit. That means in this case, first the op code is fetched and then the operands are fetched and then it is processed. While this architecture is simple to implement, it can lead to performance bottlenecks, as the CPU needs to alternate between fetching instruction and accessing the data, which can also slow down overall processing speed. In Harvard architecture, we have seen that both memories are separate and the data and instruction is simultaneously fetched. But in this case, first the instruction will be fetched and then the data will be fetched. So this makes it very slow. In summary, the Harvard architecture offers the advantage of parallel instruction fetch and data access, leading to potentially faster execution in certain scenarios. On the other hand, the von Neumann architecture is more straightforward to design and implement, but may encounter limitations in terms of performance. Both architectures have their own strengths and weaknesses, and the choice between them often depends on the specific requirement and constraints of the computing system being designed. Key features of von Neumann architecture. The von Neumann architecture, also known as the von Neumann model or Princeton architecture, is fundamental computer architecture framework that defines how computer system is structured and operates. The key features of von Neumann architecture are as follows. Single memory. Von Neumann architecture utilizes a single unified memory for both data and instruction. That means data and instruction both are stored in the same memory location. This memory is typically implemented using RAM, that is random access memory. This unified memory is concentrated, is contrasted with hardware architecture which has separate memory space for data and instructions. Then secondly, stored program concepts. In von Neumann architecture, programs are stored in memory alongside data. Instructions are represented as a binary code and can be fetched, decoded and executed by the CPU just like data. This concept is often referred to as the stored program concept and allows for flexibility in programming and running different software applications on the same hardware. Sequential execution. Instructions are fetched and executed sequentially. The CPU fetches an instruction from memory, decodes it to determine the operation to be performed, executes the operation and then moves on to the next instruction. Here in this case, first instruction will be fetched, it will be decoded and then it will be decided what operation is to be carried out. Then the data to be operated will be fetched and after execution of the one instruction, next instruction will be called. This sequential execution of instruction is a characteristics of von Neumann architecture. Then fourth is control unit. The architecture includes a control unit which is responsible for managing the operations of the CPU. The control unit fetches instructions, decodes them, controls the execution of operations and manages data transfer between memory and the CPU register. To have a precise operation, precise control, there has to be a control unit also. It will decide when to fetch the next instruction, how to execute it and how to store it. For that, the data flow, data and instruction flow, the control unit has to be there. The arithmetic and logical unit, that is ALU. Von Neumann architecture includes an arithmetic and logical unit which performs arithmetic and logical operations on data as directed by the instructions. This is a commonly done in all processors. The ALU is critical component for processing data and executing instructions. Registers. The architecture typically includes a set of registers within the CPU. Registers are small high-speed memory locations used for temporarily holding data and intermediate results during the process. We have already seen during our last lectures, during the block diagram of ALU, what is the purpose of register and how they operate. We have already seen in earlier lectures. Common register include the program counter, that is PC, instruction register IR and various general purpose register. This also we already seen in detail. Fetching and executing instruction. The CPU follows a fetch, decode, execute cycle. It fetches an instruction from memory, decodes the instruction to determine the operation to be performed, executes the operation and repeats the cycle until the program is completed. That means one instruction will be fetched, it will be decoded and it will be seen what is to be done, add, mult, subtract, whatever that, and then all these operations to be done on what, on which memory locations. then from those memory location that data will be brought, it will be operated, and once this execution is completed, then next instruction will be called. External input and output. External devices such as keyboards, displays, storage devices and network interfaces are connected to the CPU and memory via input-output, that is I/O interfaces. This is normally done in all processor and microcontrollers. These devices allow the computer to interact with the external world. Sequential access to memory. In Van Neumann architecture, both data and instructions are accessed sequentially from the memory. This is the typical characteristics, main feature of this architecture. This is no parallel operation, parallel fetching or parallel operation of data and instruction as in case of Harvard architecture. This means that there is no simultaneous access to multiple memory locations, which can lead to certain performance limitations compared to the architectures in architecture like Harvard architecture. Versatility. Van Neumann architecture is highly versatile and is well suited for general purpose computing tasks, making it the basis for most modern computers, including desktop, laptop and servers. While Van Neumann architecture has been the dominant design for general purpose computers, there are also variations and enhancement to address specific performance and efficiency challenges. However, the fundamental principle outlined above remain at the core of how most modern computers operate. Execution of program by Van Neumann machine. What is done, we'll see. The execution of program by Van Neumann machine, which addresses to the Van Neumann architecture, follows a structured process known as the fetch, decode, execute cycle. This cycle outlines how instructions are fetched from memory, decoded to determine the operation to be performed, and then executed by the CPU, central processing unit. Here is a step-by-step explanation of execution process. Program loading. Before execution can begin, the program to be executed must be loaded into the computer's memory, that is RAM. First, you have to load the program. This typically involves copying the program's instructions from a storage device like hard disk or solid state drive into the RAM. The program's starting address is usually specified to indicate where the execution should begin. Initialization. Once you have loaded the program into the RAM and specified the starting address, then you have to do the initialization. Means what? The CPU is initialized to specific state, often referred to as the reset state. That means once you have to reset, that means it will jump to the starting address, starting address of the instruction memory. In this state, the program counter PC is set to the memory address of the first instruction to be executed. When program is loaded, you have to press the reset button. That means it will jump, that time it will jump to the, or it will take the first address of the program. The program counter will be loaded with the first memory location of the address. And every time when you have to restart the program, you have to reload the program, relearn the program, you have to press the reset button so that it will get its starting address. Fetch phase. In fetch phase, program counter is incremented. The CPU increments the program counter PC to point to the next instruction in the memory. In our earlier slides, in our earlier presentation, I had given you the example of how the program counter is similar to the Viva exam. That example you must have already seen. Instruction fetch. The CPU reads the instruction from the memory at the address specified by the program counter. This fetched instruction is typically stored in the special register called the instruction register. Whatever the instruction is brought, it's kept into the instruction register. That is, this happens in instruction fetch stage of the fetch phase. Then decode phase. Instruction is decoded. That is instruction decoding phase. The CPU decodes the fetched instruction in the instruction register IR to determine the operation it represents and identify the operands if any. That means suppose a instruction is there to add memory 1 and memory 2. So after this decoding, it will decide from where I have to get the data, and then data will be brought there, that the operands will be brought there for execution. This decoding process involves interpreting the code, operation code, and any associated addressing mode or operands. As I said, in this mode, it will do the next operation depending on the instruction given, or instruction may be there, jump to this address, then it will move the program counter from to that address, or there may be push instruction. Push means what happens, whatever the address it has taken, the program counter, it will be pushed on the stack pointer, or pop instruction. That means it will get the data on the surface of the stack pointer. So depending on the instruction received and it depending on the instruction decoded and whatever the input it is getting, it will, the further operation will be performed. This is the instruction decoding stage. Then execute phase. Instruction execution. The CPU carries out the operation specified by the decoded instruction. As I said, first instruction is brought, is decoded, and depending on that what operations be done, that will be done. Either it may be add operation, subtract operation, push operation, pop operation, jump operation. This operation will be done in the execution phase. That means whatever the instruction is telling and where to be done, so that action will be taken in the execution phase. This phase may involve various activities such as arithmetic or logical calculations, data transfer between registers and memory, and control flow operation, that is branching or jumping to a different part of program. Update phase. Program counter updates. Depending on the executed instruction, the program counter may be updated to point the next sequence instruction in the memory. Suppose there is a push operation. What happens in this push operation? The program counter will push this address to the stack pointer. Or if suppose there is a pop operation, the program counter will have to take that, or say there is a return command is given, suppose, or subroutine execution is there. Suppose the program is there and while in the sequence a subroutine operation comes, go to this place, and after executing that subroutine, when the return command in that subroutine is executed, it has to come back to the program where it has, from where it has jumped. So in that case, what it will do, where the subroutine is called, that address will be pushed to the stack pointer and the address of the subroutine will be added. So this is the updation of program counter, depending on the action to be taken, depending on the program to be fetched from, or the data is to be stored or data is to be taken from, the program counter will be updated according to the instruction given. However, for certain instructions like branches or jumps, the PC may be modified to point at different memory addresses. That's what I mentioned. Suppose there is a jump address, jump to this location. So in that case, the program counter will have to load with that address, jump or maybe branch. In that case, that particular address where it has to be, where the jump has to go, where we have to jump, that address has to be loaded into program counter. Repeat cycle. The fetch, decode, execute cycle continues iteratively. The CPU repeats these steps for each instruction in the program, moving through memory sequentially. This process continues until the specified exit condition is met, such as reaching the end of the program or encountering a specific termination instruction, that is halt or end instruction. See, the repeat cycle, this whatever we have discussed so far, fetch, decode and execute, this cycle will continue until the program counter reaches to the end of the program. Or there may be instruction like halt, there is a temporary pause condition, you say, or end operations is there, or there is an interruption. So what if there is any command is being executed to stop, then till then this cycle will repeat. Termination. When the program execution is completed, the CPU may halt or return the control to the operating system or user interface depending on the context and purpose of program. Termination means once the complete program is executed, depending on the next instruction, the program will be terminated. It will be either it will halt or will stop. This is called a termination operation. The human machine's ability to execute programs in this sequential manner with the instructions and data stored in the same memory space enables it to perform a wide range of tasks, from mathematical calculations to data processing and control flow operations. This fundamental fetch, decode, execute cycle is at the heart how modern computers process and execute programs. Fetching instructions in the Numann architecture. Fetching an instruction in von Neumann architecture is a fundamental step in the execution of program. This process is part of the fetch, decode, execute cycle that the CPU, central processing unit, follows to execute instructions stored in the memory. Here is an explanation how the fetch instruction is worked. We have seen what are the phases. Now we will see in detail how the fetch cycle is working. Program counter is incremented. The process begins with the program counter, which is a special register within the CPU. First, it will read the address stored in the program counter. From which instruction is to be brought, that address will be taken from the program counter. The PC stores the memory address of the next instruction to the PC means program counter. Program counter will store the memory address of the next instruction to be executed. In the fetch phase, the program counter is incremented to point to the next sequential memory location where the next instruction is located. Memory address generation. The incremented value in the program counter is treated as a memory address. So whatever incremented address, incremented value in the program counter, whatever the data is available in the program counter, that will be treated as the memory address from where the next instruction is to be fetched, instruction or data is to be fetched. This memory address is used to access the next instruction from the computer's memory, typically from the RAM, random access memory. The CPU sends a request to the memory system to retrieve the data located at this memory address. The control signal will send a request. It may be from this memory address, you have to read the instruction. So it will send a read signal to get the data from that memory location. That data may be either a instruction or it may be a operand, opcode or operand. Memory access. The memory system responds to the CPU's request by retrieving the data stored at the specified memory address. Memory access. That's what we said. Once the address is taken from the program counter, the signal is given, then from that memory access the data will be achieved from that stored specific memory address. In the context of fetching an instruction, this data represents the binary machine code of the instruction to be executed. Whatever data you are getting, that will be the instruction to be executed. Instruction register, IR update. How the instruction register is updated. The fetched instruction is temporarily stored in the special CPU register called the instruction register. As we have seen in the block diagram, there are temporary registers for doing the operations of the execution of instructions. So whatever instruction is fetched during the fetch cycle will be temporarily stored in that register. That is called the instruction register. The IR holds the binary representation of the instruction until it is further decoded and executed. Binary, as we have seen, binary means it is a combination of 0 and 1. As we have seen, computer doesn't understand anything other than 0, the binary state. Now it will be holded till it is decoded and executed. After that, the instruction decoding is optional. It is optional because the data which is coming in may be a binary. So if it is a binary data, then you don't have to decode it. But suppose if it is stored in a hexadecimal form, in that case you will have to convert its hexadecimal code or that instruction into binary, that means in the combination of zeros and ones, so that the instruction will be understood by the processor. Depending on the architecture and the complexity of the CPU, there may be an additional step between the fetching and executing the instruction. In this step, the CPU decodes the binary instruction in the IR to determine the operation it represents and to identify any operands or addresses are modified. This stage is option because I said there may be certain things where the code may be already stored in the binary form, in the combination of zeros and one. We will see that how the mnemonics are used or how the hex files are there. These are called hexadecimal files. If it is in hexadecimal, then we have to convert it into binary. So that's why it is optional stage. The opcode, that is operation code, and any associated data may be extracted during this phase. Execution, subsequent phase. Once the instructions has been fetched and possibly decoded, it is ready to be executed. The CPU proceeds to perform the operation specified by the instruction, which could involve arithmetic calculation, data transfer between register and memory, control flow operations, and more. So depending on the decoding of the instruction, it may be a mathematical calculation, or maybe a logic operation, or maybe a data transfer. Data transfer means move this data from this location to that location, or get data from this location to this location. This is a data transfer. Program counter update subsequent phase. After the instruction is fully executed, the program counter PC is updated to point to the next instruction to be executed. This update typically involves incrementing the program counter to the address of next sequential instruction in memory. However, in cases like branch or jump instruction, the program counter may be modified to point to a different memory addresses. Yes. Normally what happens, a program counter will be ready to get the next instruction. Suppose, say for example, a instruction at location say 100, we will say a hypothetical case. At instruction at location 100 is being executed. Then next it will have to get the instruction from 101. This is logical. But suppose if the instruction says jump to 200, that in that case, instead of getting the address, instead of storing the address of 101, it will get the address of 200, because it has to jump to location 200. Normally it has to be ready for next instruction, but there is a branching or jump instruction, it will have to get the address which the program tells to get it, or where the program tells to go. So that address will be loaded into the program counter. Repeat the cycle. The CPU repeats this fetch, decode, execute cycle continuously, moving through the memory sequentially, fetching, decoding and executing instruction one by one until it encounters an exit condition, such as reaching the end of the program or encountering a termination instruction. The cycle, that is fetch, decode and execute, will continue till the end of program or the termination of the program. Fetching instructions in one Numann architecture allows the CPU to access and execute a sequence of instructions stored in memory, making it possible to run program and perform a wide range of tasks on the computer or a computer. The sequential execution of instruction is a fundamental characteristic of this architecture. In van Numann architecture, sequential operation is the fundamental characteristic. These do a sequential operation one after the another. Whereas in case of Harvard architecture, there is a parallel operation. Instruction and data are brought simultaneously. That thing is not happening here in this case, because the instruction is brought, and whatever that instruction is telling, that data will be brought. Comparison between Van Neumann architecture and Harvard architecture. Here is the comparison between the two architectures. Memory organization. In Van Neumann architecture, unified memory. A Van Neumann architecture uses a single memory space for both program instructions and data. Instructions and data are stored together in the same memory location. In Harvard, separate memory space. Harvard architectures uses two separate memory space, one for program instruction memory, and another for data, that is data memory. These memory spaces are physically distinct. There are two separate memory locations. There may be two RAMs, one for storing only instructions and one for only for data. Then parallelism. In Van Neumann architecture, sequential access. In Van Neumann architecture, instructions and data are accessed sequentially. The CPU fetches an instruction, executes it, then fetches the next one. There is no simultaneous access to the instruction and data. Whereas in case of Harvard, parallel access is possible. That means hardware in instruction allows the parallel access to the instruction and data. That means instruction is also coming at the same time. Whatever the operation is to be done on which data, the data will be also brought parallelly. The CPU can fetch an instruction while the simultaneously fetches the storing data, fetches or storing the data, potentially leading to a faster execution time for certain task. Then next, what are the advantages? For in case of Van Neumann architecture, versatility. The Van Neumann architecture is versatile and suitable for a wide range of computing tasks. Whereas, and it is simplicity. Its simplicity makes it easier to design and implement. Whereas in case of hardware parallelism, the hardware architecture can potentially provide better performance for a specific task that benefit from parallel access to instruction and data, making the processor faster. Separation. Physical separation of instruction and data memory can enhance security and reduces certain types of vulnerability. Since the data and instructions are stored separately, the chances of the security of data is better. Now, what are the disadvantages for both the cases? In case of Van Neumann architecture, potential bottlenecks. Sequential access to instruction and data can lead to performance bottleneck in some scenarios. Limited parallelism. It is less efficient for the tasks that require high level of parallelism. In case of Van Neumann architecture, the parallelism is not possible. And what are the disadvantages in case of Harvard architecture? Complexity. The need to manage separate memory spaces increases the design complexity and may require more resource. Since there are two separate memory locations, you will have to have better control unit, better space, better design, better heat dissipation. The circuit has to be designed properly to take care of all circuit design parameters. Specialized use. It may not be as suitable for general purpose computing as Van Neumann architecture is. In summary, Van Neumann architecture and Harvard architecture represent different approaches to organizing memory and executing instruction in computers. The choice between them depends on the specific requirement of the computing system, with Van Neumann being more common in general purpose computers and Harvard being favored in embedded systems and specialized applications. Harvard architecture of PIC microcontroller. Now we are going to learn PIC microcontrollers in detail in our next lectures. In this section, we will see how the Harvard architecture is used in PIC microcontroller. What is PIC microcontroller? Today, you ought to have you must have heard of the PIC microcontrollers, particularly if you are an embedded system engineer or a PCB designer. Nowadays, PIC microcontrollers are widely used in lot of embedded systems. It is a popular line of microcontroller that is currently manufactured by microchip technology. The PIC microcontroller was introduced in 1993 by the microchip, although the original chip design was created by General instruments in 1985. This PIC is now being manufactured by Microchip since 1983, but this original design was of General Instruments, who have developed this in 1985. PIC microcontrollers are made to enable simple programming and interfacing in embedded system design. Most of the PIC microcontrollers that hit the market are 8-bit microcontrollers, although Microchip did introduce some 16-bit and 32-bit PIC microcontrollers. This is the architecture of PIC microcontroller. This is the control unit, data memory, instruction memory, arithmetic logic unit, and I/O. As we have seen, there are two separate memory locations, one for storing the instruction and this is other for data. This is a bidirectional bus to flow the data in both the direction, instruction flow in both direction, and this is the data flow in both direction. This is the control unit to which gives the signal of reading or writing or fetching the data, and it is again connected to ALU through bidirectional bus, and again this control unit is also connected to I/O devices through a bidirectional bus for getting the data or storing the data. PIC microcontrollers are based on the Harvard architecture, where program and data buses are kept separate. We have seen already in the earlier diagram. Early version of PIC microcontroller uses EEPROM to store the program instruction, but have adopted the flash memory since 2002 to allow better erasing and storing the code. In EEPROM, if you use the EEPROM, you cannot change the program. If you have to change the program, you will have to first erase the EEPROM and store new data, or you will have to change the EEPROM with a new program. Whereas in case of flash memory, you can easily change the program, you can reload the program in a flash memory. Thanks to its simplicity in architecture and ease of use, PIC microcontrollers have proved to be a hit amongst hobbyists, students, and professionals. So thus the PIC microcontroller has become more popular nowadays. PIC 16F84 and PIC 16F877 were some of the most popular PIC microcontrollers with basic functionalities. Applications that require richer peripherals, higher performance, or memory can be rely on PIC 18F family. PIC microcontroller features. One of the reasons why I am such a big fan of PIC microcontroller is that they often have a similar features. This makes working with a various part numbers of PIC microcontrollers easy, as the architecture, peripheral, and design cycle are almost the same. If you change the variant of the PIC microcontroller in your design, there will not be much variation because the architecture may be more or less same. So the peripherals will be compatible with all the PIC variants. Basic PIC microcontroller may have limited peripherals, while their more advanced counterparts are rich with the communication, memory, IOs, and special function peripherals. That means the basic PIC unit has got a limited resources for input and output, but their advanced version has got more features for communication with the memories, more IO devices, and special functions peripherals like sensors, displays, actuators. Many things can be interfaced with the IO IOs, GPIOs, general purpose IO pins. However, you can expect the PIC microcontrollers generally have these features. Memory. So what is the features of the PIC microcontroller? With respect to memory, the modern PIC microcontrollers are built with a flash memory to store the program instruction. As we have discussed, since it is a flash, it becomes very easy to do the programming. Flash memory has larger capacity and easily erased compared to the EEPROM or OTP microcontrollers. PIC microcontrollers also feature built-in RAM and EEPROM that are useful in storing application parameters and runtime variables. It has got built-in RAM and EEPROM, that means this EEPROM can be electrically erased and programmed. You will also find that the special function registers and stack operators of the PIC microcontrollers are quite standard across various part numbers. Then with respect to oscillator, how is the architecture of PIC microcontroller? Like other microcontrollers, PIC needs a clocking source to drive its system timing. This is often done with a crystal or some PICs and internal oscillator. For timing purpose, you have to have some oscillator. This oscillator may be either external crystal or you can use the PIC's internal oscillators for the timing purpose. Then with respect to IO, that is input and output, PIC microcontroller labeled segregate IO pins, that is input output pins by ports, e.g. that means port A, port B. The PIC microcontrollers has got many input output pins on the ports. These pins are available on different ports like port A, port B, port C. We will see this in detail when we will be learning PIC microcontroller. What is the port and what are the IO pins, that we will be definitely going in detail during our study of PIC microcontroller. For an 8-bit PIC, a single port contains 8 individual pins. That means as on the port there will be 8 pins. Each pin can be configured as an input or output or a alternative peripheral functions. Every pin in the port can be used as either input pin or output pin or for a specific function. That means it can be used as a PWM function, or it can be used as a analog input or digital input, or it can be used as a PWM output. Peripherals. With respect to peripherals, in the PIC microcontroller, you will also find following peripherals. EU star provides a serial UART. This is a serial UART communication. That then SSP allows a special SPI and I2C communication. We will see all what are the communication protocols during our study of microcontroller. CCP, capture and compare module and PWM output. This is very important. You will be designing some comparator operator. Comparators you will be using. Suppose this temperature is this much. Suppose you have to do something depending on the your temperature data you are getting in. You get the temperature, compare it, and take some action. This is possible with the capture and compare module and PWM output. The capture and compare operation can be used for the monitoring and control system, whereas PWM, that is pulse width modulation, is used for motor control, motor speed control. ADC, convert an analog signal to the digital signal. Suppose you are getting some analog input, maybe a temperature value. This is analog. This value has to be converted into a digital form so that the processor will understand before processing it or before taking the next decision. So that ADC has to be there, analog to digital converter has to be there, that is built in the PIC microcontroller. Timers. Depending on the part number, there could be several timers in the PCs, in the PIC microcontroller. Depending on the type of PIC microcontroller, there are built-in timers for purpose, and there are a number of timers are